Hi, this is Dr. Huckaba. This is part of a lecture that I gave last semester, spring of 2020, and it covers the end of Chapter 1 and the beginning of Chapter 2, which comprises, I believe, sections 1.11 through early Chapter 2. In addition to this material, I have a small to-do list that you should think about. Obtaining access to Gradescope, which will be important for submitting your homework on time, which is due August 21st. Don't forget to work the Chapter 1 problems at the beginning of the chapter. The solution manual should come with your Klein 3rd edition as well. Begin reading Chapter 2 in Klein because this is where we're going in the next few lectures. And additionally, contact me if you're in need of any assistance with problems with the book or assignments. That includes technical issues as well. If you have an academic conflict with any exam times, if you need a letter, if you need or have a letter of accommodation from the DRC, as well as if you're having any technical difficulties in general, please let me know. Good luck.
Yes, so let's talk a bit about dipoles. I think, do I have something here? No, okay. Here, I feel like I'm forgetting something. Well, maybe not, good for me. Okay, let's talk a bit about dipoles quickly so that we can talk about molecules and their actual properties. So dipoles, maybe you remember from Gen Chem, can be very straightforward. Dipoles are essentially a unit of physics, right? They are mu, which is the dipole, and that's equal to the charge times distance, right? It's like a very physicsy equation. What we're going to do is not worry about the formula because this is not a math class. The point here is that you can look at how two atoms are bonded together and have the idea, like the fuzzy integer value that you're looking at, and think about what the dipole moment actually looks like. Because a dipole moment is something very different. If you have sodium chloride, right? The dipole moment here is essentially one full charge, so it's really a +1 and a -1 over a small area, and that's a very strong electrostatic interaction, right? That's ionic. You know, it takes water to dissolve that. If you put that into, if you contact that with an organic molecule, nothing's going to happen. It's going to stay sodium chloride. But that's not what organic chemistry is. Organic chemistry is more partial charges. It is thinking about something that has a structure like this chloroethane molecule. Now it gets a little more complicated, right? Because each of the hydrogens is less electronegative than the carbon. So every hydrogen has a small dipole pointing towards the carbon. But then also chlorine is a lot more electronegative than the carbon in comparison. So you're going to have a much larger dipole going towards the chlorine, right? And so you can't think about a molecule being one simple arrow that flows from positive to negative, because perhaps there are a lot that actually go into that. Because if you were to draw the overall dipole moment for this molecule, it would look something like this, right? And so you can't think about a simple dipole moment. You can only think about how, like, the proportion of a charge that you're actually moving across the molecule. And this is something your book, I think, tries to do a good job of, but I'm not sure that we really have to worry about the exact numbers in this class. It's more of, can you spot how the charge is moving across a molecule. You know, can you see if I draw this molecule? Can anybody see where the dipole will be there? How about we get a raise of hands if everybody thinks the dipole is going this way? Okay? What if the dipole you think is going this way? Raise your hand. Okay, we got some. All right. Anybody else have any other ideas? Maybe up? Down? No, it turns out in carbon dioxide, the dipoles are going one way and the other, which means they cancel out to give a big fat zero for the net dipole moment. Right? So this is kind of the idea of organic chemistry, is that you're thinking about how they add together. This is sort of like a destructive interference type idea in the dipole moment. Again, you can have something, and this is kind of just more for fun, you can have a really crazy structure, right? But in this crazy structure, you can see that you have two fluorines, you have two hydrogens bonded to the same carbons. These two guys are both going to be pointed towards the carbon, but man, these fluorines are going to be pulling so much electrons away that overall the dipole moment is going to be huge in one direction. So this is more of what we're trying to think about with dipole moment, is really, can you spot this? You know, it's not like, oh man, which fluorine might be a little better. No, it's seeing these simple things and applying them in future reactions. So why does this matter? Or how can you use this to your advantage? Because properties of molecules matter so much with the dipole moment, and I encourage all of you to look at the sections that deal with dipoles and the idea of polarity in the book in Chapter 1. It can really matter how you draw the structure can give you a big clue into what the dipole moment should be, so that you can get the chemistry right later. A really good example is something we already saw in the very first lecture on Thursday, and that was, I'm going to draw it like this. Sorry for these bad hydrogens. Okay, do you remember this dimethyl ether versus the ethanol? And we said that the dimethyl ether had a boiling point something like, I don't remember, it's something like -10 or something, and ethanol was 78 or something more or less. And we said that that was a huge difference because you had the difference in hydrogen bond acceptors. But what if I told you that depending on how you draw this guy, you might get the dipole moment of that molecule wrong? Because here, you notice that it looks like that carbon dioxide example, right? You have the dipole moment going this way, and the dipole moment going this way. Maybe the electrons are doing something, but it looks like it cancels, right? But if you don't know molecular geometry, what you don't realize is that what the molecule really looks like is more like this, because remember, oxygen doesn't like to make linear complexes. It has, or molecules, it has two p orbitals that push down on those two CH3 groups and cause this to be a bent structure. So really, it does have a dipole moment, and that dipole moment goes straight up the molecule because of the additive dipole moments of the carbons here and the fact that the two electrons are sitting on top up here. Does that make sense to everybody? To kind of think about geometry and be able to use it that way? Okay. All right, so you've already seen about dipoles, and this is really important because molecules in their bulk state, like as a solution, as a liquid, will actually line up these dipoles. If you have acetone, no, I did it again. This gets annoying, right, drawing all these hydrogens? If you have acetone, here you have more negative protons here, or protons, more negative electron zone near the oxygen, which means you have a partial positive on the carbon, partial negative on the oxygen, making the dipole moment go towards the oxygen, in addition to all of the carbons wanting to give their electron, all of the hydrogens wanting to give their electrons to carbon here. So you kind of have a net dipole towards the oxygen, right? And if you have a liquid acetone, they'll actually line up positive to negative, just like magnets do. If you play with magnets, you remember they have a north and south pole, right? And they always want to be attracted to one side to the other. It's the same way with dipoles. It's actually one of the most important interactions that molecules have that are not bonds. This is a non-covalent interaction. It's an intermolecular electrostatic interaction that causes molecules to have things like different boiling points, to have different melting points, to have different properties that we could find useful to us. Your book has a really nice example of acetone versus a similar molecule. Acetone has a boiling point of 56. And if you replace this double bonded oxygen by a double bonded carbon here, oh, that's a carbon, sorry. So is that. This molecule, which now that I see it is a little hard to see, but its boiling point is much lower, like -7 degrees. So because one molecule has a dipole and the other doesn't, we see this huge difference. And if you just look at the molecules, that's a pretty small difference. So we really need to remember to take these kinds of things into consideration. All right. That's not the only type of non-bonding intermolecular electrostatic interaction that we can have. There are actually a couple more, or at least a couple major ones that your book covers. Another one is perhaps one of the coolest, especially if you have an interest in biological chemistry, a type idea. It's called hydrogen bonding, and it's a very special type of bonding that occurs, for instance, in water. So if we draw water with its two lone pairs and its two hydrogens, in solution, liquid water will preferentially orient itself so that it has lined up its hydrogens and the lone pairs to make these kind of electrostatic interactions where you have a partial positive on the hydrogen because of a normal dipole, right? But then you have the partial negative that becomes from having a lone pair that actually feeds into this type of non-covalent bond. We say non-covalent because, you notice I drew those dotted lines? It's not an actual bond. It's more like the idea of salt. Again, salt is an ionic bond, but really that's a positive and a negative coming together. This is the same idea. This is a partial positive on the hydrogen and a partial negative, or nearly a full negative, on the oxygen. And this type of bonding happens between oxygen and hydrogen. It also happens between nitrogen lone pairs and hydrogen. Let's just say water again. So you could imagine if we had what maybe looks like a more complicated molecule. I'm getting ahead of myself here. So we'll say this is a complicated molecule. Glycine. This glycine could make strong hydrogen bonds with water. Also note, it can make strong hydrogen bonds with itself because it has multiple electron pairs on oxygen here and there. It has a bunch of hydrogens that can participate in hydrogen bonding because more or less, if you have any acidic proton and oxygen, nitrogen, sulfur, you can do some hydrogen bonding in solutions in water in the solid. So anytime you have NO and S and an acidic hydrogen, so we'll say XH. X can mean anything in this case. You can have some type of hydrogen bonding interaction. And this is actually the type of interaction that holds together your DNA and a lot of your proteins through secondary interactions like hydrogen bonding. So while in organic chemistry I've been showing you already a lot of molecule structures, that's really only half of the story. As you go through organic chemistry, you'll see more and more that sometimes the most important interactions aren't actually bonding. It's the idea. Yes? That is not only N or S. It's really anything that is more electronegative than carbon. So it can also be like a fluorine or a phosphorus maybe. It can be more than just N or S. But in this course and in, I guess, the real world, most often you see it between N, O, and S, just because they're the most prevalent. They're the most abundant things that we have, I guess, around us. Okay, last reason why that's important. You remember that slide in the beginning when I said what's different about water and ethanol? Water, ethanol. Now can you see what's different between these two molecules? Thinking about this set of materials we have right now. Water, 2 hydrogen bond donors, meaning the electrons go towards the hydrogen, and 2 hydrogen bond acceptors, meaning they accept electron density from another molecule. Ethanol only has 1 hydrogen bond acceptor, right? It still has 2 donors here, but it only has 1 hydrogen bond acceptors. And that may not seem like much, but we know water's boiling point to be 100. Does anybody know ethanol's boiling point? No? You can say it. It's about 78. This makes a huge difference, and this, is one reason why maybe Kentucky is a much more interesting place to live, because without this difference in polarity and dipole moment, you could not have bourbon, right? Because you could not distill water away from ethanol. So you couldn't make a spirit, and you couldn't have, a lot of the nice fancy alcohol culture that a lot of the world enjoys. So this is one very simple, nice way that organic chemistry already improves our lives, right? Because we have alcohol and bourbon because of it. All right, but more seriously, no, it's pretty serious. Alcohol is very serious. But we have one more. We have one more type of bonding that we're going to talk about that is not covalent. It's an electrostatic interaction. It's secondary. It's a lot weaker, but it still is very important. And that's called a dispersion force, or a London force. So I'll just say London. And essentially, this is like weight, this idea, this dispersion force. London dispersion is the idea of big fluffy things coming together and getting more or less stuck because it happens. It's certainly not the mathematical reason why London dispersion force happens, but it's the easiest way to remember it, because it manifests itself like this. If you have, let's say, ethane. I'm only going to draw the carbons here because it's going to get crazy in a second. If you have ethane, right? Ethane is a gas, which means that its boiling point is less than room temperature. So we'll just say it's a gas. If you have hexane, okay? No special functional groups here, just 6 carbons with hydrogens all around it. Again, I'm just drawing the carbons because that would take a long time to draw out the hydrogens. If you have hexanes, that's a liquid. And its boiling point is something like, I don't know, 60-ish. I don't remember off the top of my head. That's a liquid. If you have this molecule, C18, that is a solid. That's wax, a type of wax called paraffin wax. That's a solid with a boiling point like 500 or something. Maybe not that high. It's probably more like 400. But the idea is these molecules didn't get any extra groups. They just are bigger. There's more CH bonds there. There's just, they come together. If they come into contact with each other, they're big enough. The electrons they're the large cloud of electrons that represents all of those hydrogen, the CH bonds, are so big and polarizable that when they come together, it's harder to take them away. This is this idea, again, of partial charges, because across, because across the molecule, you can generate fairly large partial charges. With ethane, it's not easy because there's only two, but in the C18 molecule, you could imagine that you could just make some weird partial charges and maybe the molecule wouldn't realize, or it wouldn't be felt across the whole molecule. And that's the idea of London dispersion forces. Each of the forces, each of these three, the dipole, the hydrogen bonding, and London dispersion, all add up together to give a molecule its properties. I'm going to adjust this real fast. Whoa. Okay, is that better? Maybe it is. All right. They all add up together, and they're all things that we need to take into account when we're thinking about these molecules. Luckily, we aren't going to have too many examples where we have to put them all together, and it's super hard to figure out which one is dominant. Most of the time, it's going to be targeted examples that we can learn from. So don't be afraid about all three of these things coming together in a way that's super scary. But the really nice thing is that is actually the end of Chapter 1. So we've made it. This is all the review material. Congratulations. You've survived at least Chapter 1 in organic chemistry. And I think you all have done pretty well so far. Because moving into Chapter 2, you're already kind of thinking in the way you need to be if you're following along. Because Chapter 2 deals directly with communication about chemistry, about organic molecule structure specifically. Because look at what we were drawing here at the end. I just essentially gave up drawing those hydrogens, right? Because it gets really tedious. CH3, CH2, over and over and over again. Organic chemists don't do that. When we talk about molecules, we talk about them in a much more shorthand way that effectively communicates what we're trying to say and helps everybody get on the same page much faster. Now, there are two ways we do this. I'm going to show you two types, and I'll let you decide which is the most helpful. So, let's say I give you this structure. Right. Let's say I draw this. Oh my goodness, it's so tedious. Okay. I draw this molecule. C3, C3H, 1, 2, 3, 4, 5, 6, 7, 8. C3H8. I could also say H3, let me draw that in a different color so you can see where that's coming from. I could also say H3, right? H3C, C, H2, H, and then your two C's here, C, H3. Here. Do you see how that could come about? You literally read the molecule, I guess for you guys it is left to right, so that you can see what to draw next. Okay, doing this, you could perhaps even draw some much more complicated structures. Perhaps if you were pretty well practiced at this, you could even take something that looks like this. Oops. Forgot to draw out my hydrogens. Okay, hopefully you can see what that is after all my scribbles. You can even take something like this and read it out the same way. You could do, let's see, what do we have first? We have, didn't draw my hydrogen. We have H3, C, H2. I'll use the black one for the nitrogen, and CH3, 2. Okay, does everybody see how that comes about logically from the same idea? Yeah, it's called a partially, what's the word? Partially condensed structure? I think, yeah, no. Oh, I forget what that one's called. It has a name. Look in your book. It is there, but it is, I'll have it for you next week. I'm just totally blanking on it. The drawing here with the wedges and dashes, that's a partially condensed structure, meaning you've simplified some of the communication about the molecule, but you're still explicitly showing a bunch of other stuff, right? You're showing where the hydrogens are, which ones are coming out, which ones are going into the plane of the board. But still, you notice how much time that took me to draw, right? And you can imagine, too, when it comes to these, I think it's called a totally condensed structure. These, we'll call them that anyway. These condensed structures, you can imagine how that might get pretty hard to read if the molecule gets bigger, right? Because already you see different formalisms where you have H's on one side, CH2, another atom, and then some parentheses. It could really just expand. So we need a better way to effectively communicate what molecules actually look like. And organic chemists do this in a way that I really like, and that is we take these two and we combine them into what's called a bond line or line bond structure. And it's the simplest way to describe what a molecule actually is, because this equals this. Where each point here on the lines represents a carbon. You only draw the heteroatoms like nitrogen, oxygen, sulfur, halides, those things. But you never, ever draw the letter C or carbon-hydrogen bonds. They're called implicit, or that's implicit information, meaning that it's something you have to assume when you see the drawing. Okay? Explicit information is what you see here in this partially condensed structure. Everything, more or less, is there for you. You don't have to assume anything. In the bond line drawing, you do. You not only assume CH bonds, but you assume that each non-labeled atom or vertex is a carbon. So that means if you see this, right, that means you have 1, 2, 3, 4, 5, 6 vertices, 6 carbons. Each carbon should have 4 bonds, right? We're also assuming that from this structure. So you know that each carbon has 2 bonds to another carbon. Ooh, sorry. 2 bonds to another carbon. So that means each carbon has 2 CH bonds. These are things that you can assume every time. Something you cannot assume, charges, lone pairs, because I drew the lone pairs for you here on this nitrogen. but often they're left out. So whenever that's another piece of implicit information, the lone pairs are a piece of implicit information, but what is never implicit is charge, because of this reason. And this will be the last thing before we go. If I drew you this structure, okay, now we know this is C1, 2, 3, 4, H3, 6, 9, 10. Right? Does everybody follow where I'm going with that? If not, feel free to say no. Okay, we know that C3H10, C4H10, thank you. But you have to assume it's C4H10 unless I give you something like this, right? That tells you there's not a hydrogen on that middle carbon. That's a plus sign. It's missing a hydrogen. Or if I gave you this, you would know for sure that's a negative charge. But you might not get these lone pairs. But you might still have the negative charge. So you have to assume the lone pairs are there if there's a negative charge. It's missing the hydrogen. It has the electrons. It's negatively charged. Okay. That sound good to everybody? So, please remember, before you leave, think about organic chemistry before Thursday. Don't just let it sit. Go back, look at what we did. Go into Chapter 2, because we've now started it, and see how far you can get, because I bet we do pretty well on Thursday. Please remember the grade scope is due Friday this time, not Sunday. It's due Friday. I will not be available to help you for problems about grade scope if you email me on Friday night. I would love to help you any other time. So please, if you have a problem, get it figured out, because I want all of you to be able to submit your best document, no matter what the problem is. Okay. Thank you all. Have a great night. I'll see you Thursday.